Okay, welcome everyone to another video lecture series for differential calculus. Today's discussion would be on the idea of limits. Okay, so to illustrate the idea of a limit, the limit of a function, let's try to have this using an example. Okay, so given the example f of x, this is our function. This is equal to x cubed minus 2x squared over 3x minus 6. Okay, so to illustrate the idea of a limit of a function, let us first take note of the given form of the function. We have x cubed minus 2x squared over 3x minus 6. This form of a function is in fraction form, and just like any fraction, we could not allow the form of a fraction wherein the denominator of the fraction would be equal to 0. So whenever we assign a value for x in the given function, the value for 3x minus 6 could not be equal to 0. If we try to solve for a particular value of x so that the value 3x minus 6 is equal to 0, we could easily find that the value for x would be equal to 2 if we solve for x here. Obviously, if we substitute 2 in x here in the denominator, that would result into 3 times 2, that is 6 minus 6, and that would give the denominator a value equal to 0, and that makes the whole fraction, meaning the whole function, undefined. Naturally, that means that x cannot be equal to 2, and that makes 2 somewhat a limiting factor that limits the value of assignment for the value of x, since we are not allowed to substitute a value for x. But if we are not allowed to assign any value for x, are we allowed to assign any other value other than 2? The answer is of course yes. We could assign any real number for x except for 2, since that it means that the substitution of 2 produces that the function f of x is undefined. Since we are allowed to substitute any value of assignment for x other than 2, now the main concern is, what if we try to substitute values closer and closer to 2, one coming from below 2, and the other one coming from above 2. Now, to illustrate that, so that we could determine the behavior of the function f of x, let's try to illustrate that using the following tables. Now, what you can see in the table is that we have assignments for x. We have 1.9, we have 1.99, 1.999, and so on. Try to take note of the correction. This is not a comma. This is supposed to be a decimal point. So what is illustrated here is that we try to increase the value of 1.9 in such a way that we are getting closer and closer to the value 2. But since we are not allowed to substitute the value of 2 directly in our function, what we can do is to get the value of x closer and closer to 2. Now, take note of the resulting behavior for f of x. As we get the value of x closer and closer to 1.9999 and so on, getting the value of x closer and closer to 2, the value of f of x, take note that this is getting closer and closer to 1.3333 and so on. Now, of course, a running 3 in the decimal part is somewhat equivalent to 1/3, 0.333 and so on. So it is as though f of x is the value of f of x is getting closer and closer to 1 1/3, or that would be 4/3, as x approaches the value 2. Now, we can do this. We can do this for the assigned values of x lower than 2, but we could also do this for values of x above 2. That is the one that is illustrated on the right hand side of the table. We have the assignment values for x as 2.1, 2.01, 2.001, and so on, getting the value of x closer and closer to 2. Now, doing the substitution in our function, you could actually determine these values if you try to plug in or construct the equation in Excel, or perhaps you could do this manually in your calculators, and you would eventually find that the value of f of x are the ones that you can see here in the table. So again, what we can see here is that we have substituted values for x, but this time the values of x are values above 2, but getting the values of x closer and closer to 2. And again, we can see the behavior of f of x as the value of x gets closer and closer to 2. The value of f of x gets closer and closer to 1 1/3 or 4/3. Now, what this means, what this illustrates, is that if you have a limiting condition for x, it is possible that you also have a limiting condition for f of x, and this limiting value for f of x is what we call the limit of a function. Now, to further illustrate this idea, let's try to illustrate this using the graphical form. Now, first, before we proceed, take note that you have x cubed minus 2x squared in your numerator, and you have 3x minus 6 in your denominator. In the numerator, you have a common factor between x cubed and 2x squared. The common factor is obviously x squared. If we try to factor x squared from here, then we can what is left in this expression is that you have x minus 2. So that the whole numerator becomes x squared times x minus 2, as we can see here. Now, as for the denominator, the common factor would be 3. If we try to factor out 3 from this expression, then we are left with 3 times x minus 2. Now, x minus 2 could be cancelled out, so that you could cancel x minus 2 from the numerator and the denominator. Then we are left with x squared over 3. Now, if you try to graph this form of a function using, for example, a graphing calculator such as GeoGebra, you could look up this mobile app GeoGebra and try to explore this application, and you would eventually find that you could actually construct any form of a function in the GeoGebra panel, and plugging in the form of the function would produce the graph of the function. Now, suppose this is the graph of the function. Now, what is illustrated here is that if the function is discontinuous at a particular value, for example 2, that means that the graph of the function, you have a continuous smooth curve, but you will have a hole at a value of x equals 2, such as the one that is illustrated here. The function has values continuously at any given point, except at the value of x equals 2. And what is illustrated here graphically is that 2 is a limit value for x, and it's supposed to produce or point out that the value corresponding to the y value should point the limit value for f of x. Now, to illustrate this further, we could try asking the following questions, so that the answer to this question would lead us to that particular value of y, or that particular value of f of x on the y-axis, so that we could determine this value as the limit of the function. We could try asking the following questions. So, for example, as x gets closer to a particular value a, it is possible that x is not equal to a. The question now is, does the function value of f of x gets closer to some real value, number value L? As illustrated in the previous table, we know that if we try to get the value of x closer and closer to 2, our f of x gets closer and closer to a number which is somewhat equal to 1 and 1/3 or 4/3. So in our question, the answer is actually yes. As x gets closer and closer to a particular value a equals 2, but x is not equal to 2, the function f of x gets closer and closer to some real number value L. In this case, that real number value L is, we suspect that that would be 1 and 1/3 or 4/3. Now for the second question, can we make the function value f of x as close to L as we desire by choosing x sufficiently close to a, but suppose x is not equal to a? The answer is also yes. That is actually what we have done in this illustration here. We try to get x closer and closer to 2, and such that the behavior of f of x is that f of x gets closer and closer to 1.333 and so on, or 1 and 1/3. So the answer for both of these two questions is yes, and that means that the value of L exists in the given function. So if the limit exists, then that means that we could determine the value of this limit. Now, the next relevant question now is, how do we determine the value of this limit? Now, let's try to have this in a formal statement. The limit of f of x as x approaches a particular value a is represented by this expression. The limit of f of x is equal to L as x approaches L, as x approaches a. If you try to substitute the given function in this expression, our f of x in the given example is x cubed minus 2x squared over 3x minus 6. Then the form of the function of this expression becomes limit of x cubed minus 2x squared over 3x minus 6 as x approaches 2, where a is equal to 2, is equal to 1 and 1/3 or 4/3. Now, what we have done here is that this is somewhat based on suspicion. We did not actually make any procedure of determining the actual value for f of x for a given value of x as x. For example, if x is equal to 2, what we have done earlier is that we have illustrated it in terms of computing for the value of f of x for each instance of assignment of x either below 2 or above 2. But later on, as we progress in this topic, we will be having an actual procedure of determining 4/3 as x approaches 2 without going through the process of assigning values for x every time and determining the behavior of f of x. Okay, so before that, we try to have the formal definition of the limit of a function. So let's have the formal definition. Okay, so let f be a function defined on some open interval containing a, except possibly at a itself, and L be a real number. And that is illustrated in the example. In this expression, you have limit of f of x is equal to L as x approaches a. Try to make the correction. This is supposed to be x as x approaches a, not z. Okay? So, to continue, given this definition, this means that for every positive number epsilon, this is the symbol for epsilon, there exists a number delta. Delta is also a number, a positive number, such that the absolute value of x minus a is greater than 0 but less than delta, then f of x minus L is less than epsilon. Again, I'll be stating this slowly. The formal definition of the limit of a function. Let f be a function defined on some open interval containing a, except possibly at a itself, and L be a real number. Then we have the limit of f of x is equal to L as x approaches a, means that for every positive epsilon, there exists a positive delta, such that if the absolute value of x minus a is greater than 0 but less than delta, then the absolute value of f of x minus L is less than epsilon. Okay, what I have done is that I just read you the definition, but I'll be presenting to you the definition part by part and try to illustrate it using a diagram in order for us to understand what is meant by the parts that were presented in this definition. Okay, so let's have this diagram to illustrate the definition of the limit of a function. Okay, now try to look at the x-axis. You have here a particular value a, and the blue line here represents your function. That is our f of x. This is the graph of the function f of x. Now, at a particular point A, this vicinity here wherein we have x and we have the red arrows, this is what is meant by x approaches a. X approaches a, the approach could be coming from above a or below a, just like what we have illustrated in the table here. The value a equals 2 could be approached from below 2 or above 2. Okay, so if a is a real number, then the approach to a could be done one coming from above a and one coming from below a. Now, what is meant? What happens in this approach is that we define this approach to some open interval. So, meaning this point here on the x-axis and this point here in the on the right-hand side of a and the the left-hand side of a defines our interval. That is the part wherein we have in the definition the function f defined on some open interval containing a. So that means we could find a within this vicinity, and this is the open interval. Okay, where do we find the value delta? Delta is positive. Delta is actually a number wherein we define the distance of the points of the open interval. So meaning at this point here on the right hand side of a, the distance from a up to this point is actually the distance delta. Delta is a number, that number is positive. So for example, if delta is equal to 1 and for example a is equal to 2, then this point here above a is equal to the point 3, since delta is equal to 1. That's just an example. Now, so for example, delta is equal to 1 and a is equal to 2. That means that this point here is actually 2 minus 1 is equal to 1. But of course, the value of delta is arbitrary. That means we could assign any particular value, any value for delta, for as long as the value for delta is positive. Okay, so that means if you have a within the open interval, the interval would be defined as a minus delta and a plus delta. That is our we call that the delta neighborhood around a. Okay, so where in the definition that we could find that neighborhood defined using delta? it is actually the part of the definition in the if condition. We can see here that if we have the statement if x minus a is less than delta or greater than 0, this part of the definition is actually the definition that we have illustrated here. Although it's not written here that this part is actually delta, but this is actually the distance delta from a. Okay. Now, what is epsilon posited here in the part of the definition? Where do we find this number? Epsilon is a number. Epsilon is positive. Now the question is, where do we find epsilon positive in our diagram? Okay, so try to listen carefully. Now, what we have done here is that we have defined delta as the distance around a, above and below a. Now, what that means is that a portion of the function would fall within this particular defined open interval. So the value of f of x would be now defined within this point and within this point. Now this point is actually on, if we take that on the x-axis, on the y-axis, we could find on the y-axis that the value of this point on the y-axis is about here. And the value of the function f of x on the lower part within this interval is somewhere here. And the value of this point corresponding to a on the x corresponds to a particular value on the y-axis. And we define this point on the y-axis as L. So that means this point here at the middle between these 2 points is L. Above L is this point, and below L is this point. Okay, so I am encouraging everybody to make use of your imagination. So since we have a faulty illustration, perhaps we could find a simpler illustration, but with a complete label. But let's try to continue. Okay, so again, we have the value of L on the y-axis, and we could find L somewhere here. We could find the value of f of x on the y-axis at this point, on this point, and we can find the lower value of L at this point lower than L. Now these 2 points above and below L is defined also by this open interval as we have defined before in terms of the distance of delta from A above and below. Okay, so try to imagine at this point from L up to a point Y above L, and from L to a point Y below L. The distance from L above and from L below is actually our distance epsilon. So the distance epsilon here is actually the distance above L from here up to here, which is also the same distance from here up to here. So going through the definition again, knowing now what is meant by epsilon and delta, that means if you have a function f defined on some open interval containing a, except possibly at a itself and L be a real number, the limit of f of x is equal to L as x approaches a, means that for every positive epsilon, there exists a positive delta, such that if the absolute value of x minus a is less than delta but greater than 0, then f of x minus L is less than epsilon. Okay, since epsilon and delta defines distances from L and the distance from around A is the distance delta, and the distance around L is epsilon. What is meant by this if and then statement means that we could find A around the vicinity of, or the neighborhood of delta If we could find A within that neighborhood, we could find L within the neighborhood of epsilon. That is what is meant by the definition of formal definition of the limit of a function. For a given function defined on some open interval, for a given delta, for a given epsilon, we could find delta around the given vicinity A, so that the limit of f of x at A is equal to L within the given neighborhood.